The past 10 weeks has been filled with grueling hard work. Our team worked many days and nights to help our robot achieve peak performance. It wasn't easy, but our hard work paid off. For week 8's challenge, we finished 3rd. And for week 9, we were very close. Our robot was just short of a few inches from completing the challenge. Our team experienced many ups and downs, so let's ask our members about their proudest achievements.
This is McFlurry. We call him that because we ordered too many McFlurries while we were staying up doing this job. My role on the team is the hardware engineer, as I configure all the hardware related stuff as well as the STM related code. My job is just to configure the robot so that it receives command from the UART communication, and then it executes the task accordingly. Dealing with hardware can sometimes be very challenging and compromising. For example, this IMU chip on board does not function very well while there is massive current around it. To accommodate for that, I've implemented a hybrid control algorithm that takes into account the parameters such as gyroscope reading, encoder data, and so on. While the robot is steering, it not only measures the aggregate angle it deviates from its original position, but also measures the encoder readings such as the inner wheel travel distance and the outer wheel travel distance, and calculate the turning radius in real time, such that our robot will be stable enough to carry out all the tasks.
For algorithms, we use the A-star algorithm to achieve point-to-point path generation, and using A-star we computed the various path costs between all the goal states in the problem and solved the shortest Hamiltonian path by finding the optimal permutation. So Xinghao, what is your favorite algo feature?
My favorite part is our clever obstacle detection algorithm. We noticed that the safety distance between the robot and obstacles was a crucial balancing act. Playing it too safe would cause our robot to move very inefficiently, while having too little clearance would cause the robot to hit more obstacles. This little piece of overlooked logic controlled how our robot handled risks and was key to our winning algorithm. Gim, what about you?
For me, it will have to be our balancing act between optimality and physical robot movement precision. Due to hardware limitations, our robot did not move symmetrically and some movements caused more deviation than others. However, favoring some movements more would cause the solution to lose optimality. Through rigorous testing, we managed to fine-tune the algorithm to find the right balance that allowed us to trade a tiny bit of optimality for a whole lot of movement accuracy. I think this logic definitely helped us clear the challenge reliably.
Hi, we are the computer vision team. For every image class, we captured multiple images under different environments and lighting conditions, following which we labeled the images and performed augmentation in terms of rotation, crop, blur, and also shearing. This gave us a total set of 12K images, which we used to train the custom YOLO V5 model using 100 epochs. After validation and testing, we obtained a final model with average 95% accuracy for detection.
Hi, my name is Kai Kiet and I'm responsible for integrating the image recognition with the RPi. So how does it work? Firstly, the RPi will capture an image and send it to a local CV server through a HTTP post request. After that, the server will process the image and send back the ID to the RPi.
We are the Android team. Our Android application user interface allows for easy placement of obstacles, which can be dragged around quickly and efficiently. Removing obstacles is rather simple too. It can be accomplished by dragging the obstacles out of the grid map. Additionally, the user can easily modify both obstacle ID and its direction based on their needs. For added convenience, the user can also choose to preload the grid with default 6 obstacles. This feature streamlines the obstacle placement process, enabling users to reduce setup time for the week 8 challenge.
When the user has done setting up the obstacles, we can send the obstacle properties to RPi by pressing the Send Map button. Our app includes a timer feature that allows users to track the duration of their challenge run for both weeks. Additionally, we have implemented 6 movement buttons that correspond to the different movement options such as forward, forward left, forward right, backwards, backwards left, backwards right. These buttons provide precise control over the robot's movement, enabling users to optimize for the most accurate and tight turns possible.
In our group project, the Raspberry Pi serves as the central hub for all communication processes. It effectively integrates Android, algorithm, computer vision, and STM components. We employed threading and lock mechanisms to guarantee seamless communications between these devices. A unique feature I've implemented is a 2-tier instruction queue system, which facilitates the appropriate division of instruction sets during image capture. The first tier comprises the STM queue designed on the Raspberry Pi. In contrast, the second tier allows the algorithm and computer vision components to acquire images at the right moments. Additionally, I incorporated various features that facilitated individual testing. For instance, the system could accept live instructions or positions on demand. This approach consistently maintained a secure and robust design, effectively addressing most use cases.